Start coming down here, Larry. All right, so there's an interesting story with this talk. The great Nick Wan was running a competition. So he's Cincinnati Reds, but he was doing a competition with, you're all right, stay alive. It's the theme. Larry's a PhD student, so that's his theme right now. But he did this competition with, and Larry's going to talk a bit about this, but MLB released new data this past year on swing length, bat speed information. And so it was a competition hosted on Kaggle, and originally Nick had made an offer to the winner to cover the hotel costs to speak at to attend our conference. And I thought that was pretty cool, but I thought, oh, it'd be even better if like the winner of that competition would be able to present at the conference. Now Larry's going to present, but he's not the winner. The first place of the competition took a computer and was like, no, I don't want to go to the conference. Then the second place turned it down. Didn't get a response from the third place. And eventually the fifth place person, Larry, said yes. Yeah. So Larry is a fourth-year PhD student in neuroscience here at Carnegie Mellon University, which made it very convenient for like, oh, sure, Larry can talk, because Larry's actually also an active member in our sports analytics research lab. So Larry was one of the members of our Big Data Bowl finalist team. This guy has attended more Pirates games than I think. When I interned there and had to work in the room, I think he passed me this year. Like I was there every day effectively. So he is obsessed. He loves Pittsburgh sports, always brings a positive attitude for everything. So I'm going to turn it over to Larry here, and he's going to give you his presentation on what he did for this competition. All right, so let's give a big round of applause for Larry.
Yeah, I think
it would help if I share the screen here.
Oh. All right. Thanks for the introduction, Ron, and thanks for having me here. Yeah, that'd be great. So, all right. So the work I'm going to talk about today is called Features Importances in Predicting Batting Ball Outcomes, which is from a Kaggle-based approach. The data I'm using in this work is from this Kaggle competition organized by Nick Wan. This is his picture. So he's the head of the analytic department for Cincinnati Reds. And in this competition, we are interested in using the bat tracking data and pitching data to predict the probability of each batting ball outcomes. And more importantly, we want to know how the interaction between bat tracking and pitching data influences the prediction of batting ball outcomes. The data set only includes pitches that were hit in the fair territory. So unfortunately, this beautiful pitch by Paul Skeens against Shohei Ohtani is not in the data set because Shohei could not put it in play. Happens a lot. So yeah, so it's all the fair balls during the regular season games in the 2024 MLB season up to the All-Star break. So there are like 50,000 pitches in the training set and 14,220 pitches in the test set. And the outcome in this data set include out, single, double, triple, and home run. Error is not being included in the data set. And as you can see from this bar plot, majority of the batted ball, around more than 60% of them, ended up being an out, and less than 1% of them ended up being a triple. So this is telling us we are dealing with a multi-class prediction problem, and the data set is imbalanced. And I'm not sure how familiar you guys are to the competition on Kaggles, but the way Kaggle evaluate the model performance is quite interesting, I would say. So in this competition, the prediction is evaluated with 1 versus rest area under curve score, and there's a public leaderboard and a private leaderboard. The public leaderboard is available throughout the competition. The AUC score is calculated with 5% of test data. So what happens really often in the competition is that the participant is going to adjust the model based on the AUC score on the public leaderboard. And the private leaderboard is not available until competition is over. The AUC score is calculated with 95% of test data, which is a way bigger data set compared to the public leaderboard. So the consequences which happen a lot in lots of the Kaggle competition, is that making modifications solely based on the public leaderboard could lead to overfitting. So in other words, you want to build something that's flexible enough, but also like robust. All right, so we have already went over the purpose of the competition, as well as how the model performance is being evaluated. We can now talk about the features. And as Ron mentioned previously, over the summer of this year, the MLB released a bunch of bad tracking data that came from some, I would say, 8 of the high frame rate Hawkeye cameras in the MLB ballpark that track the location, speed, and path of the bat when the batter is swinging at an incoming pitch, which exactly like the video is showing here. So right at the moment where the bat made contact with the pitch, like right here, we're able to get the bat speed and the swing length of the batter. The bat speed is being described as how fast the barrel of the bat travel upon making contact with the ball. And the swing length is being described as a distance between the start of swing to the impact point. So if a batter whiff at a pitch, it's going to, I believe, calculate the distance between the barrel and the closest contact to the ball. And in addition to all the bat tracking data, we also have other features such as the pitch quality, including the velocity, spin, extension, and acceleration of the pitch. Batter information, not included the batter's identity and their height. And the bat tracking data, like I mentioned previously, and game situation, excluding the ballpark information, as well as batted ball direction described by the spray angle. So in total, there are 36 features. And across the competition, there are numerous features being derived by different Kaggle contributors. And here I'm just showing you some example of the top rated notebooks. I highly encourage you to go through them because like Isaac Newton say, standing on the shoulder of a giant is great, and standing on the shoulder of a bunch of stacked giants is even better. So as a result, like looking across these notebooks, we have 91 features in total. And when we look across all the features by their data type, we will see that 80 of them are numerical features and 11 of them are categorical features. So, which means the data set is like eventually heterogeneous. And the results of this heterogeneous data set is that there are definitely a few caveats into taking into account before we throw it into a machine learning model to try to make a prediction. The first caveat is that categorical features could increase sparsity. So when we look at the number of unique value in all the categorical features, we found 9 of them being a binary categorical features, which is nice. We can eventually just use a dummy variables to replace it. But there's this one feature, namely pitch type, that have 13 unique values. So in this situation, simply create a bunch of dummy variables by one hot encoding can introduce columns with sparse information, because as you see, forcing fastball happen like 30% of times, but some pitches like knuckle curve happens less than 5% of times. So in this case, there will be one column that's have a bunch of 0 and just occasionally 1 or 2 1 show up, which is not really helpful in terms of for the model to make a prediction. And the second caveat is that the batters and pitchers' handedness often leads to bimodal and multimodal distribution. Bimodal and multimodal distribution can introduce higher risk of overfitting, especially in model with higher flexibility, because those kind of model eventually trying to capture every single nuance of the distribution. And there are actually plenty of features in the feature set that have this multimodal distribution. I'm just going to show you one prime example, which is spray angle. So as we can see in this plot of spray angle, right-hand batter tend to have the spray angle with a negative value, while the left-hand batter tend to have spray angle with positive value. The main reason behind that is, as we know, batter tends to pull the ball to generate the maximum power. And pulling the ball for right-hand batter, meaning hitting the ball closer to the third baseline. And for left-hand batters, it means hitting the ball closer to the first baseline. So in this scenario, that the handedness actually introduced ambiguity in interpreting this common behavioral trait shared by different batters. So as a result, we need to adjust the features based on the handedness to ensure they are interpreted consistently for both left-handed and right-handed batter. So one way to do it is just, for the left-hand batter, just multiply their spray angle by -1, and eventually you get a unimodal distribution in this case. All right. So previously, I have already covered the task we want to do and the features of the data. So we are looking at a heterogeneous data set. And we are doing a multi-class prediction with imbalanced classes. And we want to have some interpretability with the data. So the model we eventually want to build should handle categorical variables reasonably well and handle imbalanced data as well as provide fair assessment of the imbalanced multi-class prediction. And in addition, it can also conveniently calculate the feature importances and interaction. So in this situation, I just reside to categorical boosting. The other name of that is called CatBoost. So categorical boosting is a gradient boosting technique, but what separates it from traditional gradient boosting technique is that it can automatically handle categorical features with order encoding. Order encoding, the main idea of that is that for each categorical features, it will calculate the main target value based only on the previous rows within the current permutation. And the final encoded value is average across all permutations. So that's one thing that separate CatBoost from other modeling technique. The second advantage of that, it can prevent target leakage by order boosting. So order boosting is a really complicated process, but to boil it down, the main idea is similar to order encoding, that each data point is predicted based only on the data that was available before it. And the data set will randomly permute it after each boosting iteration to prevent overfitting to the order. All right, and eventually, in CatBoost, the feature importance can be calculated based on the change in the model's prediction when the feature is included in each split of the trees. And one way you can do it, basically rank the feature is to feeding all the features into a CatBoost classifier and generate the features importance ranking as a process of feature engineering. So here I'm just showing you the top 10 ranked features based on the feature importances. And the green square, the features circled by the green squares are those derived features. So as you can see, 7 out of 10 of the top 10 features are actually derived features, which showcase the point that sometimes the original features may not be the best for you to use in the model prediction, and you need to do some engineering before you put it in the algorithm. And eventually, I just put the top features into a CatBoost model and then optimize the hyperparameter using Optuna, which is a really good toolbox for you to optimize the model. And in the beginning, the public score doesn't look really good. The AUC score is 0.719 and ranked me like 27th place. And then I'm like, well, that's the best I can do. So I just wait after the deadline. And then once the private leader review, once the prediction was compared with 95% of test data, the AUC score boosts all the way up to 0.757, which ranked me 5th. And that's how I ended up here. So it's cool. The model demonstrates good generalization, and it's not overfitting, which is exactly what we want. And after that, there's a question that is lingering me. Is that this model is doing well, but is that really interpretable? Like, is it really make sense? So I just recited this a feature interaction value, which is calculated user shapely interaction value, which is something that coming from game theory, and quantify the interaction effect of two features. Well, in this case, I and J, by averaging the weighted difference in the prediction score across different configurations of a feature subset. So the subsets here are the subsets of features include I and J, subsets of features include either I or J, and subsets of features without I and J. And I think earlier someone mentioned that this is an analytic conference, so I'm also going to include a formula here. And the formula actually directly depicted how the feature interaction value is being calculated. So you have the prediction score of subset of features with I and J, and then you're going to subtract the prediction score of the subset feature with I or J individually, and then you plus the prediction score of the subset of the features without both features to basically isolate the effect of the pair of features. And eventually you want to take the weighted factor to allocate the impact of the pair of features, and then eventually you calculate the average. All right, so what I'm showing you here is a resulting network plot of the feature interaction. Each notch here indicating the top 10 features, and the connection, the width of the connection actually indicating the Shapley interaction value. And with this network plot, I then calculated node strength by taking the sum of the Shapley interaction value of the nodes. And the top 5 strongest nodes are relative height, the horizontal location of the pitch, and the launch speed, swing plane efficiency, and horizontal spray effectiveness. So when we boil down the features together, this feature relationship actually showcases that how the batter cover the horizontal plane of the plate is important, which aligns with our expectation of a good batter. So the main takeaway for me from this competition is that Kaggle is great. It provided great generalization in predictive batting ball outcomes. And the feature relationship within the model actually reveals the batter's ability to maintain contact quality across horizontal plane of the plate. It's the key indicator of batting ball outcome. However, there's definitely some limitation here. It doesn't include the ballpark information like I mentioned previously, or the fielder's route selection. So here is just a little question, like, can anyone try to guess which ball hit in, like there are 2 scenarios, both have a similar launch angle, exit velocity. Which one of them actually ended up being a hit? Shout it out. B, all right. So it's funny because these two scenarios actually happened like 2 days apart, and it's actually by the same batter named Mookie Betts. So unfortunately for Mookie, the ball hit in scenario A is a home run, but not in scenario B. And the main reason is really simple. The left field at the Petco Park is shorter than Dodger Stadium. So this also brings up a future question, is how important is the ballpark information in the prediction and how it fit into the feature interaction network? So that's basically what I have for the talk. At the end, I want to show my gratitude to Nick Wen for organizing this great competition. It provides opportunity for people like me to learn about different machine learning algorithms as well as working with baseball data, and also other Kaggle contributors. And I learned a lot from their notebook. Without them, I can't achieve this achievement. And at the end, I really want to show my gratitude to the Carnegie Mellon, the Sports Analytics Center, especially Ron and Kwon for their feedback of the talk. And thanks so much.
All right. Thank you, Larry. We are going to now take a 10-minute break, and then we come back for our reproducible research competition.